the next Year 11 Math Methods video. This one's going to be on logarithms. Basically what a logarithm is the opposite, or more precisely the inverse of an exponential. So let me show you what I mean by the inverse of an exponential. It means if we have an equation that's y equals a base a to the power of x, it means we can write that as a logarithm. That in fact implies that if we take the logarithm with the base a, so the same base, and we do that logarithm of the answer y, that becomes x. So these two things are equivalent. So notice the base is written there. The answer y is now the variable, and the variable x is now our new answer. Okay, so another way of thinking about this is a more precise way is actually that logarithms. So I'm just going to write logs. They're the things. They are the things that undo exponentials. And deals. They're the things that undo exponentials. In other words, if you have log to the base a of a to the power x, the log to the base a and the a to the power of x sort of cancel each other out. So the log undoes the exponential, and you get x out as your answer. In a very similar way, if you have a to the power of log base a x, the exponential and the log, they undo each other, so they sort of cancel out if you like, and the answer there is x also. So these are just sort of, here the logarithm comes first, here the exponential comes first. Either way, they undo each other. So let's do a couple of examples just to get the hang of understanding logarithms. So here we could say that, that if we have 2 to the power 3, that equals 8. That means, or it implies, that logarithm with base 2 of 8 must be 3. So in other words, we're finding this exponent 3 there. Okay, let's do one more example. Let's say we want to find the logarithm of the base 10 of, say, 10,000. That's the same thing as saying, and we're trying to find what that equals. Well, we know that what we're doing is 10 to the power of some unknown thing, x. So this will equal x, an unknown. So 10 to the power of x equals 10,000. 10,000. And you know that obviously 10,000 is 10 to the power 1, 2, 3, 4. So it's 10 to the power 4. 10 times 10, 4 times to get our 4 zeros. So therefore our x is 4. So that answer is 4 there. Okay, let's do another bit of an example with something like this. So let's suppose we have, I don't know, 6 to the power of 6 to the power of x equals, let's do an easy one, equals 36. Well, what you can do to find what x is take the logarithm of base 6 to both sides. So you can say logarithm base 6 of this side of 6 to the power x equals logarithm to the base 6 of this side, 36. Now here the logarithms to the base 6 and the 6 to the power of x, they cancel each other out. So you have x equals logarithm of 6 of 36. Now we know that 36 is just 6 to the power 2. So obviously the answer is going to be 2. But at this point, if you want to, you can use your calculator. So taking out our calculator, we can find the log. Here it is in blue, so we'll press Control Log. And at first it's asking us for a base, so our base is 6. And we wanted the log base 6 of 36. And there we go, our answer is 2. Now, quick note with calculators, our CAS is really handy because we can put in any base. But on a normal scientific calculator, you have to use the base 10 because that's the only one they've got, pretty much. Now this is a really handy feature in case the equation is a bit more difficult. So imagine if your equation is actually 6 to the power x equals, say, 250. Now x is no longer going to be a whole number. So what you can do is take the logarithm to the base 6 of both sides. So you'll get x is logarithm to the base 6 of 250. So notice here I'm sort of skipping this step for this particular question. So x is logarithm to the base 6 of 250. Let's get out the calculator again. So this time we're doing logarithm base 6 again of 250. There we go. Oh, it's given us the exact answer, which is the same thing. So we want the approximate answer, the decimal answer. And here we go. It's roughly 3.08159. So x is roughly 3.089 or something like that. So in other words, 6 to the power 3.089, whatever it was, equals 250. So there we go, there's the very, very basics of logarithms. Alright, let's get some more space here. Alright, so we know that if we have a to the power x equals y, that implies the logarithm to the base a of y equals x. Okay, so what if we had a to the power 1? Well, a to the power 1, no matter what this base a is, the answer is going to be a. It's going to be the same thing. So that implies logarithm to the base a of the same number equals 1. Okay, so there's our first sort of little neat trick, if you like. So that's the first one to remember. Now, the second thing is, you know that if we have a, any number, to the power of 0, that equals 1 from our index law. So that implies our second trick, log to the base a of 1 equals 0. Okay, so there's our second sort of little trick, if you like. Log to the base anything of the number 1 equals 0. Okay, another little thing to note is that when we did our a to the power x equals y, we noted that a had to be larger than 0, because otherwise it wouldn't work. You'd have square roots of negative numbers. So because the logarithms sort of follow from exponentials, we have this same bound, so a must always be greater than 0 as well. Secondly, also just like the index laws, or the indices have index laws, logarithms also have a couple of special identities called the log laws, or logarithmic laws. And there's 3 of them. So what I'm going to do is just list them and show some examples of these laws. And in the following video, I'm going to prove these laws. And that video will be an optional one, but one you might find interesting. So here are the laws. First up, if you have logarithm to the base of a certain number, let's call it a, of a number times another number, then you can actually break this up into 2 logarithms. You can have logarithm, now these logarithms have to have the same base, so they all have to have the base a. So logarithm of this first number, m here, and then add on logarithm, same base again, a, of n. Okay, so that's the first log law. Now, the second log law is very similar to the first, but with division. So if we have log to the base a of m divided by n, that is the same as doing log to the base a, so same base, m, so the numerator, the top one, minus log to the same base a of n, the second one. So here order is important. You make sure the negative sign comes before the denominator here on the bottom. Okay, now we're up to our last law. Our third logarithmic law says that logarithm to the base a. Now, if you have a number m to the power of another number n, what you can do is take that n outside as a multiple, as a factor if you like. So that will equal n, this exponent, times logarithm to the base a of m. Okay, so these are our 3 log laws, and you're going to be getting these stuck in your head by using them again and again. So let me do an example of each one. Okay, first example. Example 1. Suppose we have log to the base 3 of, let's say, 6. And then we add on log to the base 3 of 13.5. What we can do is use our first log law. So notice that the base is the same as both 3, and so we can multiply m by n. So we've got logarithm base 3, 6 times 13.5. Now here you can use your calculator to do the 13.5 multiplied by 6. 6 5s is 30. Oops, 3. 6 3 is 18 plus 3. And 6 1s plus 2. So it's 81. So that's log to the base 3 of 81. And that will give us log to the base 3 of, now 81 is just 3 to the power 4. Now if we want to here, we obviously know that the answer is going to be 4, but what we could do if we wanted to is use log law number 3 and say the 4 is going to come out the front because it's an index there. So what you could do is put the 4 out the front and go 4 log 3, and now we've just got 3. Now remember this little trick up here, where log, if the base here is the same as our answer, then we get 1. So log to the base 3 of 3, this bit here is 1, so we're left with 4 times 1, and that equals 4. So there's our first example done for us. Okay, let's do another example. Example 2, simplify. Simplify the following. Let's suppose we have 2 times log base 4 of 8 minus log base 4 of 2, let's say base 4 of 4. Okay, so what we're going to have here, we've got 2 options. You notice the log to the base 4 of 4, that's just going to be 1. But for now, I'm not going to, I could do it in that order and it would work out, but let me not do that. Let me instead say, I'm going to put this 2 using this law, I'm going to put the n up as an index. So we have log to the base 4 of 8, now this 2 is coming to the top here, 8 squared, and maybe I will actually, oh no, I'll leave this as minus log 4 of 4. Okay, now this is 8 squared is 64. So we've got log base 4, and this one is 8 squared, 64. Now here I've got minus, and the base is 4. So I can use this trick number 2 to divide by n. So I'm going to divide 64 by 4. Okay, so that will give me log to the base 4 of 16. Now, hopefully you know that 16 is in fact 4 squared, so the answer therefore will be 2. And we're done with that example as well. So a quick note on this example 2, there are multiple ways to do these questions. So if I wanted to, I could have started this whole thing off by saying that this bit here is actually 1, if I had wanted to, and then done the other things as well, and I would have also got the same answer of 2. So you can try that yourself to prove that these can be done multiple ways. Okay, now what we're going to do is we're going to use logarithms to solve equations. So here there's no new theory. All the theory's been covered. All we've got to do is a couple of examples to show you or give you confidence perhaps at how to do these. So we're up to example 4. So here we're now solving instead of just simplifying things. So first example, solve log to the base 5 of x equals 3. So what we're doing with this fairly basic example here is we're going to change it into exponential form and say that this is this sort of implies, oh no, what I'm going to do is I'm going to do the power, I'm going to take the exponential of these. So I'm going to do 5 to the power of this side and 5 to the power of that side. So what happens here is the 5 cancels out with the log to the base 5. So on this side we're left with just x, because the exponential undoes the log, or vice versa. And on this side we have 5 to the power 3. And we're pretty much done. 5 to the power 3 is the same. 5 to the power 3 is 125. You can do that bit on your calculator if you want to. Okay, let's do another example. So example 5. Let's say we have, so we're solving again. And this time we'll do one only a little bit harder. So log to the base 5 of 2x plus 1 equals 2. Okay, so we're going to make the same start. This time I'll skip a step. So if we want to undo the log to the 5, we'll take 5 to the power of both sides. So on this side we'll have 2x plus 1, and on this side we'll have 5 to the power 2. So we've undone the log to the power to the base 5 there. Now 5 squared is 25. Next we're going to get rid of the plus 1 by doing minus 1 to both sides. Minus 1 to both sides. So that's 2x equals 24. Now we'll divide both sides by 2 and get x equals 12. Okay, next example. Example 6. Okay, this one we'll have, so we're solving again. Solve 10 to the power x minus 3 equals 1 million. 6 zeros there. Okay, so what we're going to do here is take the logarithm of both sides. So here I'm taking the logarithm, log to the base 10 of this side, 10x minus 3, and logarithm to the base 10 of this side. Okay, so now we have on this side the log and the exponential cancel out, and we're left with x minus 3, and on this side we've got this logarithm here, log to the base 10 of a million. So here at this point, this one's actually pretty easy, but just to give you a bit of extra knowledge, I'm just going to solve this using my CAS. So here we go, just in case this is necessary, log to the base 10 of 1 million. There we go, the answer is 6. So back we go, so that equals 6. Now adding 3 to both sides gives x equals 9. There we go, finished example 6. Alright, let's get a little bit more room. Okay, the next couple of examples might get a tiny bit harder. Example 7. Okay, example 7 should be a tiny bit harder maybe, so let's see. Log to the base 2 of 2x plus 1 minus log to the base 2 of x minus 1 equals 4. Okay, so the first thing you should notice is that we've got a log to the base 2 here and a log to the base 2 here, and there's a minus sign. So this is our second log law. So for this one, because they're minusing, we can do a division here. So it all equals log to the base 2 of the thing that's positive, so 2x plus 1, divided by the thing that's negative, x minus 1, equals 4. Okay, now I can't really simplify this stuff very easily anyway, so let's get rid of the log to the base 2 by doing 2 to the power of both sides. So then we get 2x plus 1 on x minus 1 equals 2 to the power of 4. Now 2 to the power of 4 is just a number. It's 2 times 2 times 2 times 2. By the way, here's a trick way to do this. 2 times 2, that bit's 4. 2 times 2, that bit's 4. So then we've got 4 times 4, which is 16. So that might be a bit of a handy hint for you. Now what I'm going to do is, here we've got to divide by x minus 1, so I'm going to do times x minus 1 to both sides. So there we go, I've gotten rid of it from this side, put it onto the other side by multiplying. Okay, now I'm going to expand this bracket out here, so that's 16x minus 16. Okay, so I'll subtract the 1 from this side. Now I'm going to plus 17 to this side, so the plus 17 is going to go to this side, but I'm going to subtract 2x. So that'll give me plus 17 over here, and over here with the now minus 2x will give me 14x. So now I'm going to divide by 14, gives me x equals 17 divided by 14. So it's a weird number, that's what happens sometimes. So that is our final answer. Okay, I think I've got one more example for you. Example 8. Let's have log to the base 3 of x minus 1 plus log to the base 3 of x plus 1 equals 1. Okay, so for this one, we notice that we're adding two logarithms where the base is 3. So this is our rule number 1 here. So let's use rule number 1 where we multiply these bits here. So this will give us log to the base 3 of x minus 1 and multiplied by x plus 1. That all equals 1. Now let's get rid of this log to the base 3 business by doing 3 to the power. So on this side the log 3 will disappear, giving us x minus 1 and x plus 1. And here we've got, on this side, we'll have 3 to the power of 1, which basically is just 3, so we can sort of forget about that. Okay, so let's expand these brackets out now. So this gives us x squared plus here we've got plus x, then we've got a minus x, and then we've got minus 1 equals 3. So I'll take away 3 from both sides, which gives us x squared. These two have cancelled each other out. Minus 4 equals 0. So x squared equals 4. Now that means that x equals plus or minus the square root of 4, which equals plus 2 or minus 2. So x could be plus 2 or it could be minus 2. Now the thing here is that these values in here, these values in here have to be greater than 0. That was mentioned earlier. So this one we have to check, is x minus 1 greater than 0? Well, it is if it's x is plus 2, because then this will be, if we have plus 2 minus 1, that equals 1, which is greater than 0. But if we put in minus 2, that's minus 2 minus 1, which is minus 3, which is not greater than 0, so that's no good. And for this one over here, similar thing happens. For plus 2, we're above 0, but for minus 2, we're below 0. So the minus 2 does not work, it's not in the domain, so the answer must be plus 2. There we go, that's the final example, the hardest one. Best of luck, and well done for sticking with this video all the way to the end.